Hi class, this video is going to finish up section 8.4. So this is part B of section 8.4. We're going to cover the last three learning objectives. And really the focus of this part of the section is on unit vectors, and we're going to talk about two special unit vectors referred to as vector I and vector j. So first of all, we have here just the definition of what a unit vector is. So a unit vector is a vector that has a magnitude of 1 unit, right? So it has a length of 1 unit. So if you look here at this box, if you want to find a unit vector in the direction of a given vector, you do the following, right? So if you have a vector v that has the components a, b, then a unit vector, we'll let that be u sub v, and the direction of v is given by the following. So basically what you're going to do is take the vector that you have, v, and divide it by whatever magnitude that is, right? And that will in turn give us a vector that is in the same direction, but has a length, a magnitude of 1, right? So you can see here there's a couple of different formats that we can do, in order to get that, right? So initially, you can see the last part here. What you can do is just take the a component divided by the length of v, then the b component divided by the length of v, and that will give you that vector that you're looking for, right? So to practice this, example 1, we want to find a unit vector in the direction of v equals 5, negative 1, right? So the very first thing I would do is look for the modulus of vector v. So this is going to equal, right? And just a note on some notation. So remember we do the double bars for the modulus of a vector. But oftentimes, given the context, a lot of people will just use just absolute value bars. So just instead of doing the double bars, just do the single bars, but they mean the same thing. So just note that. And then also, just a quick notation thing, reminder, is if I put a bar above v, that's the same thing as putting an arrow symbol for a vector, right? So because we can't really show boldface when we write it. So either one of those things are okay and pretty acceptable to most mathematicians, right? So to find a unit vector in the direction of v equals 5, negative 1, right? We were starting out by finding the modulus, the magnitude of vector v. So this would be equal to, remember, the square root of a squared plus b squared, right? So here, remember, this is in the form a comma b. So a is 5 and b is negative 1, right? So if we just plug those in, we get this. So this becomes the square root of 25 plus 1, which is the square root of 26, right? So then to find this unit vector in the direction of v, we would take just take the a component divided by the magnitude of v, right? So I could write this out. So we're looking at it in terms of this form. So this would just be equal to 5 divided by radical 26, comma, negative 1 divided by radical 26, right? And if you really want to, you could rationalize the denominator for each of these. So we would need to multiply both by radical 26 over radical 26. So this would give me 5 radical 26 over 26, comma, negative radical 26 over 26, right? So this is one possibility for an answer, or this would probably be okay too, right? So either of those in the box would be appropriate, right? So then now we're ready to introduce I and j. So these are two important unit vectors. So I is equal to 1, 0, and j equals 0, 1, right? So these are unit vectors in the direction of the x-axis and the y-axis respectively, right? So in other words, if you just want to see, if this is, a coordinate system, we'll say a comma b, right? Then I would just look like this, right? And j would look like this, right? So I is just one unit in the x direction, and j is one unit in the y direction, positive y direction, right? So I have stated here that the importance of I and j is that any vector can be expressed as a linear combination of I and j, right? So I can show this, right? So if I say, let vector v equal a comma b, right? Then what we have is vector v equals a comma b, which equals, this would be the same thing as if I took a comma 0 plus 0 comma b, right? So vector addition, right, kind of doing that backwards, that would still give me a comma b. So then what I could do is pull out a factor of a, oops, this would be 1, plus, and then I could pull a factor of b out of the second vector. And then notice that 1 comma 0 is just I, and 0 comma 1 is j, right? So basically what we've just shown is that vector v can be written as ai plus bj, right? So that's what we mean by, so any vector can be written in terms of I and j, right? So that just makes it convenient and nice to work with, right? So then that information is just summarized here in this table, right? So you can read over that. So then example 2, we want to practice this. So we have, the vector 12 comma negative 1, and we want to write this in terms of I and j. So 12 comma negative 1 is just the same thing as the a component, which is 12 times I, plus the b value times the vector j, right? So this would be the same thing, of course, as 12I minus j, right? And if you want to see this kind of visually, let me get some graph paper here. All right. So we'll let this be the a axis, the real axis, and b the imaginary axis. So then, so we want to graph the vector 12 comma negative 1, right? So if we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and then negative 1, right? If I put a dot there, then the vector that connects, goes from the origin to there would be the vector that we're looking for. Right? So notice that, it's like going, so if these blue vectors are I, then I used 12 of those, right? So this, in other words, represents the 12i. And then this part is like we went downward but that's like negative j. Right? So if we combine 12 i's and one negative j because we're going downward, then that's how we get to that vector, right? So that's why that's useful to get to that point. Right? So then the next one here, whoops. Oh, and just a correction. So this, I should have actually let this be the x-axis and this be the y-axis, right? So I apologize. I think I mentioned A and B and then was saying that, A is the real axis and B is the imaginary axis. So that's actually when we're dealing with complex numbers, a complex plane, but these vectors aren't necessarily in the complex plane. So just make that correction. Sorry for that error. Right, hopefully, I guess I made that same mistake here too, so sorry about that. I guess my mind was still on the complex numbers section that we covered recently. Right. So if we were in class, you guys probably would have been yelling at me about that, so sorry. All right, so then part B, we're given vector A equals negative 9.4i plus 7.1j, and vector B equals negative 0.6i plus 3.2j. We want to write negative 2 times vector A minus 4 times vector B in terms of I and j. Right? So I'm just going to write this out, negative 2a minus 4 times vector B. And it turns out what we can do is just plug in the values for A right, and B. Right? So I can just distribute the negative 2 through, and then we can combine like terms, right? Just like we typically would. So you can think of vectors I and j kind of like being variables, right? So so negative 2 times negative 9.4 would give me 18.8i, and then negative 2 times 7.1 would be negative 14.2j, and then we take negative 4, whoops, that should be negative, right? Negative 0.6, yep. So if I take negative 4 times negative 0.6, we get plus 2.4i, and then negative 4 times 3.2, we get minus 12.8j. Right? So then now I can just combine like terms, right? So this one and this one are like terms, where I can combine those and get 21.2i, and then this one and this one we can combine to get minus 27 times j, right? And we want to keep that in terms of I and j, so that's what we're looking for, right? So not too complicated, right? All right, so then the next objective, objective 5, is being able to relate component, form, and direction and magnitude of a vector. So we have just some information here. So if we let v be the vector AB, be a vector in standard position. So remember, standard position means that the vector's at the initial points at the origin. And if we let theta be between 0 and 360, be the direction of v, measured counterclockwise from the positive x-axis. So how we've been measuring theta the entire class. The following things are true. So the magnitude of v is still a squared plus b squared, the square root of all of that. So the square root of a squared plus b squared. And remember, we can find theta by using tangent, the trig ratio tangent. Right. So this, this side is b units, and this side of the triangle is a units. So remember SOHCAHTOA, right? So tangent is just the opposite over the adjacent, right? And of course, a can't be 0 because we can't divide by 0, right? So that's going to give me the magnitude and direction for vector v. And then we can actually calculate a and b by using cosine and sine, right? So, for example, I could get cosine of theta equals the adjacent over the hypotenuse, which is the magnitude of v. And then I can multiply both sides by the magnitude of v and get a equals magnitude of v cosine of theta, right? So that's where that can come from. And then I can do something similar to get b, right? So you can see where those come from. So then if I plug those values in for a and b into this equation here, we can get these this vector form, right? Or in other words, this would also be true, right? So this last bullet point is just plugging things in for what we've seen, right? So then just some terminology. So a vector representing the displacement of an object is called a position or displacement vector. A vector representing the speed and direction of an object is called a velocity vector. And a vector representing the force acting on an object in a given direction is called a force vector, right? So common units of forces are pounds, newtons, and dynes. Force vectors are often denoted by capital F, right? And bold, that means for a vector, or W for weight, or T for maybe tension. So those are just some common notation in the sciences, like in physics. So we have some application problems to work through. So example 3, it says a man exerts a force of 80 pounds on an object by pulling on a rope at an angle of 30 degrees from the horizontal. Write the force vector v in terms of I and j. Right, so we can work through this. So the first thing, just a note, so this force of 80 pounds, what that tells me is the magnitude of vector f is equal to 80 pounds, right? And this measurement is theta, right? So I know that theta equals 30 degrees. So we want this in terms of I and j, right? So in other words, we want to use this format, right, that I highlighted in green here. So vector f is going to be equal to the magnitude of f times the cosine of theta times vector I plus the magnitude of f times sine theta times vector j. Right? So if I plug in what I know, the magnitude of f is 80, so this would be 80 times cosine of 30 degrees, right, theta, and then times I, plus 80 times sine of 30 degrees times vector j. Right? And of course, right, I can make my 30, 60, 90 triangle really quick. So across from 30 is 1, across from 60 is radical 3, the hypotenuse is 2. So then I can plug these values in. So cosine of 30 would be radical 3 over 2 times I. And then this would be plus 80 times, so sine of 30 would be 1/2 times vector j, right? So this equals 40 radical 3 times I plus 40 times j, right? So in other words, f, the vector f, is equal to 40 radical 3i plus 40j, right? So that's what we are looking for. So we found the force vector f in terms of I and j. Right? So in example 4, we have a ball is thrown from a height of 1 meter. At the time of release, the velocity of the ball is given by v equals 27.2 I plus 12.7 j, where each component is given in meters per second. Find the initial velocity v sub 0 and the angle theta above the horizontal in degrees at which the ball was thrown. Round to 1 decimal spot, right? So it turns out the initial velocity is going to be equal to the magnitude of vector v. So this would be equal to the square root of, so we would take 27.2 squared plus 12.7 quantity squared, and this equals the square root of 901.13, and this is approximately 30.0 meters per second, right? So if we round to 1 decimal spot, right? So then what I need to do next is to find theta. So remember, tangent of theta equals b divided by a, which would be 12.7 divided by 27.2, right? So in other words, inverse tan of 12.7 divided by 27.2 is going to equal theta. And make sure your calculator is in degree mode, but this should come out to be approximately 25.0 degrees. Right, so those were the values that we were looking for, right? So you want to be comfortable with those equations for the vectors. Right? So then I think I mentioned this before in the previous video, but just a reminder that if you see like a vector r, this is often referred to as a resultant vector. And this essentially is the vector after some operations have been done, right? So for part A, actually for example 5, what we're going to find is the resultant vector is equal to the plane speed plus the wind speed, right? So this kind of equation, right? So what we have is that a plane travels with an airspeed of 400 knots at south 20 degrees east and encounters a wind of 50 knots acting in the direction of south 30 degrees west, rounding to the nearest whole unit. We want to express the velocity of the plane p relative to the air in terms of I and j, and then the same thing for the wind w vector, right? So first of all, let me just kind of draw the vector. So this is, north, south, west, east. So when you see south 20 degrees east, that means, think about as you're going south, and then you're going to go 30 degrees in the east direction, right? So this part, whoops, that's not 30, that's 20, right? I was looking at the wrong one, right? So this one I circled is south 20 degrees east. So you're going 20 degrees towards the east direction, right? So that's just kind of a visual picture, if you will. So if you want to find the velocity of the plane, we need to find the magnitude of the p, right? And we know that to be 400, right? 400 knots from there. And then what we also need to know to get the vector in terms of I and j is we need to know theta, right? So theta is going to be equal to 270 degrees plus 20 degrees, right? Because, here is 270 degrees, right? Because, here's 0 going around that way. That's what theta is, right? So we need to take 270 plus 20 degrees to get 290 degrees. So now that I know the magnitude of vector p and I know theta, I can now find the vector. So the vector p is going to be equal to the magnitude of p times cosine theta of vector I plus the magnitude of vector p times sine of theta times vector j, right? So then I can just plug in the values that we have. So we'd have 400 times cosine of 290 degrees times I plus 400 times sine of 290 degrees times vector j. Right? So then we can get, by plugging that in my calculator, we can get at some decimal approximations. And we're asked to round to the nearest whole unit. So if we take 400 times cosine of 290 degrees, rounding to the nearest whole unit, that comes out to be approximately 137. And then, 400 times sine of 290, we get 376 times j. Right? So that's what we are after. Right? So if you want to put the vector in terms of I and j, we need to know the magnitude and theta. Right? So then part B is we want to express the velocity of the wind in terms of I and j. Right? So the information for the wind is here. We have 50 knots, and there's the direction. Right? So if we want to draw a quick picture of this, we're going south 30 degrees west, so that means we would have this picture. Right? So if I want to find, theta really quick, that would be equal to 270 degrees minus 30 degrees, right, which is 240 degrees. And then we also know that the magnitude of vector w, right, so this is vector w. See, this was vector p up here. So the magnitude of vector w is equal to 50 knots, right, because that's the speed, right? So then now what we would have is that vector w equals the magnitude of vector w times cosine of theta times vector I plus the magnitude of vector p times sine of theta times vector j. So this would be equal to 50 times cosine of 240 times I plus, whoops, I wrote p here, that should be w. Right? So and that would be plus 50 times sine of 240 degrees times vector j. So then we can get some decimal approximations here again. So we want to get to the nearest whole number. So this turns out to be negative 25i minus 43j. Right. So there's approximation for w. Right. So then part C, we want to find the speed and the bearing of the plane. Right. So basically for this one, all we need to do is note that the resultant vector is going to be the plane, speed of the plane, and plus the speed of the wind. Right, so this is going to be approximately, because we rounded these values. So vector p was 137 times I minus 376 times vector j. And then vector w was negative 25i minus 43 times vector j. So this equals, so just combining like terms, so this would be 137 minus 25 times I plus negative 376 minus 43 times vector j, which this equals 112i minus 419j. Right? So this is vector r. Right? So then the speed, the ground speed, is going to be equal to the magnitude of vector r, which is equal to the square root of 112 squared plus negative 419 squared. So if we simplify this, this comes out to be approximately 434 knots. Right, so that's one answer that we were after. the next thing we want to find is the bearing. So to be able to find the bearing, we need to find theta. So remember, we can use tangent of theta equals b divided by a. Well, the b value is negative 419, right? That's here. And then the a value is here, which is 112. So in other words, if I take arctan of negative 419 divided by 112, that's going to equal it's going to equal theta. So plugging this in your calculator, you get theta is approximately was it negative 75 degrees, right? So then, if we go negative 75 degrees, that means that there is 15 degrees on this side, right? Because they're complementary. They're going to combine to be 90-degree angle, 75 and whatever this missing angle is, right? So the bearings of that would be, so we're going like southern, so this would be south, 15 degrees, east, right? Because we're going south, but then going 15 degrees towards the east direction, right? So this would be the bearings, which is the second part, right? So we have both parts now, right? So let's try the next one. Example 6. So Joe enters a triathlon and must swim to a buoy offshore and then back again. A current of 0.5 miles per hour flows due west. So if Joe starts at the closest point J on the shoreline to the buoy B, in what direction theta should he swim in order to arrive at the buoy? Assume that Joe's speed swimming in still water is 2.5 miles per hour, round to the nearest tenth of a degree, right? So there's a diagram missing here that I'll draw for you. Right, so here's, the shore, and then out here is the buoy. Let that be point B, and then here's J. So this is going straight north, right? And then so this would be the resultant vector, and then we're swimming out this way, where this is theta, and this is vector v. And then we have this water current that's going directly towards the west, right? So we'll call that vector C for the water current, right? So we can get some information about some of these vectors. Like vector C, notice that it's only going in the like the x direction, right? And it's going negatively, and the magnitude of that is 2.5. So, the water current is 0.5, right? So this would end up being negative 0.5 times vector I, right? That's going to be vector C, right? Because you just have the x coordinate and you're going to the left, so that's a negative value. Then the magnitude is 0.5. Right, so that's vector C. And then vector R, the resultant vector, that's going straight north, right? So that's going to be in the form 0I, because we don't have an x component, plus k times j, right? Where k is Joe's actual speed, right? So in other words, k equals the magnitude of r, right, which is Joe's actual speed. right? So then the magnitude of vector v is equal to 2.5 miles per hour, right? So that means that vector v is going to be equal to 2.5 times cosine of theta times vector I plus 2.5 times sine of theta vector j, right? And that's just using some of the forms presented before, right? So we have this information so far. And I should just make a note, let vector v equal Joe's velocity in still water, and vector c equals the velocity of the water current. Right. All right. So what we can do now is to come up with an equation, right? So let me change the color here. So in other words, what we know is that the resultant vector is going to be equal to the vector v plus the water current vector, right? So if I just plug in the parts that I know, the vector r is 0 I plus kj equals, and then vector v is 2.5 cosine theta times I plus 2.5 sine theta times vector j, and then we'd have plus, so that's vector v, and then vector c is negative 0.5 times vector I. Right? So then in order for, when two vectors are equal, remember their components have to be the same. So in other words, it might be convenient if I just look at the horizontal components, the parts with an I, to solve for theta, because that's just going to be equal to 0. So in other words, what we can gather is that 0 times I equals 2.5 cosine theta times I minus 0.5 times vector I, right? So again, this is just the fact that the horizontal components must be equal, right? So then what we're trying to do is solve for theta, right? So that's all we're trying to do for this part. So then what we could have now is I could actually divide both sides by vector I, right? Because this would be 0 times I equals 2.5 cosine of theta minus 0.5 all times vector I, right? So just factoring out vector I. And then if I divide both sides by vector I, that would give me that 0 must be equal to 2.5 times cosine theta minus 0.5. And then now trying to solve for cosine theta. So if we add 0.5 to both sides, right, what we end up with is 0.5 equals 2.5 cosine theta, and then divide both sides by 2.5. What I end up with is cosine theta equals 0.2. So then arc cosine of 0.2 equals theta, which equals, so putting that in your calculator, you get roughly 78.5 degrees. Oops. Right. So that's part A. And then part B, we're trying to find the true speed, right? So remember, you know, that Joe's true speed is the vertical component k, right? So basically what we can do is we can make a true statement using the vertical component part, so everything that has a vector j in it, right? So just like part A, we're just focusing on the one of the components. So in order for, you know, this equation to be true, you have to have kj equal to 2.5 times sine theta times vector j, right? So similarly, we can, you know, divide both sides by vector j. Oops, not a capital J, a little j. And that gives me that k must be equal to 2.5 times sine of theta. So then k would be equal to 2.5 times sine. And we know what theta is from before, which is 78.5 degrees, right? So this comes out to be 2.4 miles per hour, right? It's rounded to one decimal spot. So k equals 2.4 miles per hour, right? All right, so now we're going to look at some more applications from physics. Right, so in many applications of physics, we encounter systems with numerous forces acting on an object. So if forces F1, F2, F3, all the way to Fn act on an object, the sum of the forces is called the resultant vector, right, R. So we have here, you know, the resultant vector is going to add up all the forces together. So with example 7, we have a diagram, and we're told if the magnitude of F1 is 32 pounds, the magnitude of F2 is 24 pounds, and the magnitude of F3 is 15 pounds, write the resultant vector in terms of I and j. Right? So essentially what we want to get at is the resultant vector equals F1 plus vector F2 plus vector F3, and we want to figure out what this is in terms of I and j. Right? So our whole goal is really going to be to find the values for A and B. Right? So that's our goal. So to be able to do that, we want to be able to write F1, F2, and F3 in its trig form, and then be able to add those vectors together, and then finally we'll get the values for A and B out of that, right? So first we need to find the theta for each force vector, right? So in other words, so using the picture, we get directional angles 4. So for vector F1, right? So from here to here, that's just 90 degrees. And then for F2, we get so F2 is here, so we're looking for this directional angle. So that would be 90 degrees plus 68 degrees, right? Plus this 68. So that gives me 158 degrees. And then lastly, for F3, that's going to be equal to, so we're going this way, so that would be 360 degrees minus 40 degrees, which is 320 degrees, right? So we need to know all of those. And then, F1, vector F1 is going to be equal to the magnitude of F1 times cosine of theta times vector I plus the magnitude of F1 times sine theta times vector j. Right, so this equals, so the magnitude of F1, we're actually told here, right, is 32. So this would be 32 times cosine of, and then we want this directional angle, 90 degrees, times I, and then plus 32 times sine of 90 degrees times vector j. Right? So then, cosine of 90 degrees is 0, so this would be 32 times 0 times vector I plus 32 times, and then sine of 90 is 1, so this would be times 1 times vector j. So this is just going to be equal to 32 times vector j. Right? So F1 equals 32j. I'll just put a box around that so we can get to that easy. So then we need to do some work for F2. So F2 is going to be equal to the magnitude of F2 times cosine theta times I plus the magnitude of F2 times sine theta times vector j. Right, so the magnitude of F2 is here, 24 pounds, right? So this would equal 24 times cosine of, and theta for this is here, 158 degrees. Right, so then we'd have plus 24 times sine of 158 degrees times vector j. Right, so then just using my calculator to simplify that, that gives me, so I'm rounding to the nearest tenth, would give me 22.3 times I plus 9 times j. Right? So we'll need to have that handy. And then lastly for F3, this would be the magnitude of F3 times cosine theta times vector I plus magnitude of F3 times sine theta times vector j. So the magnitude of F3 is here, 15, and there's a theta we need, right, 320. So this would be 15 times cosine of 320 degrees times vector I plus 15 sine of 320 degrees times vector j. And this would be approximately 11.5 I minus 9.6 j. Right, so again, just round to the nearest tenth. So then we know the resultant vector is equal to F1 plus F2 plus vector F3, which equals 32j plus negative 22.3 I plus 9j, and then plus F3, which is 11.5 I minus 9.6j. Right, so we can combine like terms. So this would become negative 22.3 plus 11.5 times vector I plus 32 plus 9 plus negative 9.6 times vector j, which this becomes negative 10.8 times vector I plus 31.4 times vector j. So there's the resultant vector. Right? And that's what we're asked to do, right? Put it in terms of I and j. Right. All right. So the last example here is using an application with what we call static equilibrium. So we're told here, suppose that forces F1, F2, F3, all the way up to Fn act on some object. So the object is said to be in static equilibrium if the resultant vector force is the zero vector, right? So the 0 vector is a boldface 0, and this just has the vector component 0, 0. In other words, is 0 times vector I plus 0 times vector j. Right, so this is what we call the 0 vector. Right. So in this one, it's actually going to take a little bit of work. So probably have to write some things on the back of this page. And I know I needed an extra page to fill out the solutions. Excuse me. But basically, what we're going to be doing is trying to get some equations, and then we're going to have two unknowns, which is T1 and T2, and we're going to have to use a system of equations in order to find those, essentially. Right. So we have this diagram, and the scenario is that two cranes support a 1-ton, 2,000-pound crate in static equilibrium as shown in the figure below. The figure is not to scale. And then find the magnitudes of the tension vectors T1 and T2 round to the nearest pound. Right. So what we're after, the goal, is to find the magnitude of T1 and the magnitude of T2. Right. So another thing to note is that if I make my XY axis here, this degree measurement, this theta for T1 is going to be 45 degrees. And then, this angle measurement would be 90 plus 30, or 120 degrees. Right? So what I could do is I could write, vector T1 is equal to the magnitude of T1 times cosine of 45 degrees times vector I plus the magnitude of T1 times sine of 45 degrees times vector j. Right? So then vector T2 would be the magnitude of T2 times cosine of, that would be 120 degrees times vector I plus the magnitude of T2 times sine of 120 degrees times vector j. Right? And then vector W, the weight vector, we already shown here, is negative 2,000 times vector j. Right? And that makes sense because it's going, the weight is going straight downward, so it only has the vertical component, and since it's going down, it's negative, and we know the magnitude of that is 2,000 pounds. Right? So we could say that we know that vector W plus vector T1 plus vector T2 is equal to the 0 vector, and that's since it's in static equilibrium. Right, so just filling in these values, we get negative 2,000 times vector j plus the magnitude of T1 times cosine of 45 degrees times vector I plus the magnitude of T1 times sine of 45 degrees times vector j. Right? And then plus, we need T2, so that would be the magnitude of T2 times cosine of 120 degrees times vector I plus the magnitude of T2 times sine of 120 degrees times vector j. Right? And that's equal to the 0 vector. Right? Which, instead of writing 0 vector, we could just spell that out as 0 I plus 0 j. Right? So again, kind of like what we did let's see, was it in the previous example? That was, I think, 2 examples ago. Yeah, example 6. Remember that when you have an equation where 2 vectors are equal, they're only equal if their corresponding components are equal, right? So in other words, if we just look at the horizontal components, so everything with the i's, right, we could get the following, right? So in other words, the magnitude of t1 times cosine of 45 degrees plus the magnitude of t2 well, we don't really need that parenthesis. Won't do that. Plus t2 times cosine of 120 degrees. Well, yeah, I'll put parentheses all around it, and then times vector I must equal 0 times I. Right? And I'm going to refer to this as equation 1. Right? So in other words, these were the horizontal components, right, from the equation above. Right? And so now we can look at the vertical components. So that would be negative 2,000 plus magnitude of t1 times sine of 45 degrees plus magnitude of t2 times sine of 120 degrees. This all times vector j must be equal to 0 times vector j. Right, I'm going to call this equation 2. And as I said, these are the vertical components. So then if we simplify equation 1, we're going to get so cosine of 45 is radical 2 over 2, right? So we're going to get radical 2 over 2 times the magnitude of vector t1 plus, and then the cosine of 120 degrees is negative 1/2. Right, times the magnitude of vector t2, and that's going to be equal to 0, right? So initially, all I did is substitute values, appropriately into the cosine, 45 degrees, and cosine of 120, and then I divided both sides by the I vector, right? So we get that to be simplified, and I'm going to refer to this as equation 3. And then we can also simplify equation 2 to get negative 2,000 plus, so same idea, simplifying it the same way. Right, and I'm going to refer to that as equation 4. Right, so I divided both sides by vector j, and then substituted values in for cosine of 45 and sine of 45 and sine of 120, right? All right, so now what I want to do is pick on equation 3, right? So I'm going to solve equation 3 for the magnitude of vector t1, right? So I'd have radical 2 over 2 times t1 plus negative 1/2 times vector t2. That's equal to 0. So one nice thing I could do to start with is I could multiply both sides by 2. So then what I'm left with is radical 2 times the magnitude of t1 plus, essentially minus magnitude of t2 equals 0. And then I can add the magnitude of T2 to both sides to get radical 2 times the magnitude of T1 equals the magnitude of T2. And then divide both sides by radical 2. And that gets me the magnitude of T1 equals magnitude of T2 times 1 divided by radical 2. And then I can multiply this times radical 2 over radical 2 just to simplify this, which gives me, this would be radical 2 over 2 times the magnitude of T2. Right. So in other words, what we have, the magnitude of T1 is equal to radical 2 divided by 2 times the magnitude of T2. Right, so we need to keep this, and I'm going to refer to this as equation 5. Right. So now what I can do is I can substitute equation 5 into equation 4 to get the following. Right, so we're solving a system of equations using the substitution method. Right, so this would be negative 2,000 plus radical 2 over 2 times radical 2 over 2 times the magnitude of T2 plus radical 3 over 2 times the magnitude of T2. That's equal to 0. Right, so I could add 2,000 to start with. Right, and notice I only have one variable now. I just have, the magnitude of vector T2. Right, so that's what I'm trying to solve for. So this gives me, and I'm going to go ahead and multiply these two things together. So that gives me radical 4 over 4 times the magnitude of T2 plus radical 3 over 2 times the magnitude of T2. And that's equal to 2,000. And then radical 4 is 2, so this just becomes, 2/4, which is 1/2, right? So this would be 1/2 times the magnitude of T2 plus radical 3 over 2 times the magnitude of T2 equals 2,000. So now I can add these together. So this becomes, and I have common denominator, so this would be 1 plus radical 3 over 2 times radical T2 equals 2,000. So we could multiply both sides by 2 to make this a little easier. So we get 1 plus radical 3 times the magnitude of T2. And that's equal to 4,000, right? 2 times 2,000. And then divide both sides by 1 plus radical 3. So radical T2 is equal to 4,000 divided by 1 plus radical 3, which is approximately equal to 1,464 pounds. Right? So remember what we were after is the magnitude of T2 and the magnitude of T1. Right? That was our goal. So we found the magnitude of T2 to be 1,464 pounds. So then to find T1, I just need to plug that into my equation, right? So before, we already found that the magnitude of T1 was equal to radical 2 over 2 times the magnitude of T2. So that's equal to radical 2 over 2 times 1,464, which is approximately equal to 1,035 pounds, right? So 1,035 pounds. So those two values are what we were after, right? Whew. Right, so that problem was, a lot of work doing solving system of equations by substitution, but you could do it, right? All right, so that's all I have for this video. So make sure you let me know if you have questions. Thanks.